Hi, welcome back. In this lecture, I would like to discuss a topic that I'm pretty much sure that you already heard about. That is quantum supremacy. I want to define what we intend with the quantum supremacy and all the experiments that have been conducted in the last few years and also all the debate that this experiment generated. So let's start with this lecture. So where the term quantum supremacy comes from? Well, the term quantum supremacy was first coined by Preskill in 2012. So there is a very important article called Quantum Computing and the Entanglement Frontiers that introduced the term quantum supremacy. But what quantum supremacy means? Well, quantum supremacy refers to a computational task that can be efficiently performed on a quantum computer beyond the capabilities of the state-of-the-art classical supercomputers can efficiently implement. So it's a computational task that cannot be efficiently computed by classical supercomputers. Note that there is a big caveat. The task refers to any computational task that meets these criteria, not necessarily a useful one, right? So that's an important point. So it could be a benchmark, not necessarily something that is targeting a specific application. In general, the quantum supremacy is a significant milestone for a researcher and a scientist working on quantum computing. So it gives us a reference point where we are when comparing quantum computing to classical technology. Obviously, quantum supremacy has implications for cryptography, optimization, and scientific simulation. As I told you, give us reference points where we are in terms of computing capability when using quantum computing. If you heard about the term quantum supremacy, you probably heard about it in connection to the famous Google's quantum supremacy experiment. So the Google research team, together with the collaborators, argued to have achieve the quantum supremacy in a 2019 paper published by the Nature journal that I show here on these slides. I saw in the slides the title, the paper called Quantum Supremacy Using a Programmable Superconducting Processor, a major team mainly by Google and the NASA team. I also put on these slides one of the leaders of this experiment, Sergio Boico, from the Google team. So what this team did? Well, they used a 53-qubit superconducting quantum processor named Sycamore. The specific computational experiments involve a specific random quantum sampling circuit that is a kind of a benchmark that a classical computer or a supercomputer can find very hard to simulate. It turns out that the Sycamore quantum computer completed the task in 200 seconds, where a supercomputer would take 1,000 or years, and that's what is claimed in the 2019 Nature article. So this is a benchmark that is possible to do in 200 seconds on a quantum computer with 53 qubits, and will take more than 1,000 years to simulate the same thing on the supercomputer, according to the Google's estimate. I want to spend a few words about this specific benchmark called the random quantum circuit sampling. Sampling from the output distribution of the quantum circuit is one of the most natural problems to demonstrate quantum supremacy. It turns out that increasing the number of qubits, the amount of memory that we need to simulate on a supercomputer the same problem scales exponentially, right? So we do not have enough memory in a supercomputer. So to simulate this task on a classical computer one must perform all the linear algebra and matrix computation to determine the final state of the wave function representing our quantum computing system. However, a quantum computer naturally performs these calculations by simply evolving in time the physical realization of the quantum gates. So it's something very easy for a quantum computing, but if you want to emulate the same operation, a classical computer will take a lot of linear algebra, matrix computation, and particularly a lot of memory. So this is a benchmark. It doesn't have a direct application, to a science problem. And today, this random quantum sampling circuit is an established benchmark. So for instance, if you use the CIRC Google Quantum Computer Simulator, but also interface to the quantum computer, you can actually prepare the quantum circuit quite easily. You decide the depth of the circuit, and then you use a function to basically generate the quantum circuit associated to the supremacy experiments at Google. And here on the right side of the slides, you can find a simple diagram of this quantum circuit sampling. I will spend a little bit more about this particular benchmark, hopefully by the end of the course. The announcement by Google to have achieved the quantum supremacy spurred a lot of controversies and debates. So one of the major critiques was that the chosen task, that is this quantum random sampling circuit, does not have an immediate practical usage. Right? It's not used for solving any scientific application. In addition, also there was a major critic, especially from the researcher at IBM, that the quantum computer simulator on classical supercomputer can actually simulate in a reasonable time the random quantum circuit using 53 qubits. On the 21st of October in 2019, in fact, as a reaction to the Google's paper, IBM announced that by using the Summit supercomputer at the Oak Ridge National Labs, we can actually simulate the same problem on a classical supercomputer using 2.5 days. Right? That is not hundreds of years as claimed by the Google paper. IBM also argued that the threshold for quantum supremacy has, for this reason, not been met, and there is further work to do to still show that quantum supremacy is achieved. Other colleagues also emphasize the importance of these results, and importance that these experiments highlights quantum computers' potential and accelerates quantum research. So in these slides, I put the paper from IBM discussing the simulation of the quantum random sampling circuit using 54 qubits. This is the last slides of my lecture. I just want to summarize a few things. So quantum supremacy is a stepping stone for quantum computing that give us where we are in terms of capabilities, especially compared to classical computing. A number of different challenges lay ahead of us. So for instance, we do need to address the problem of error rates and qubit stability. So we do need improvement when it comes to error rates and qubit stability in order to enable practical application. In fact, many researchers, including Google ones, for instance, are working on fault-tolerant quantum computing algorithms and error correction. Most important, this is extremely important for us, achieving useful quantum computation remains the ultimate goal of all researchers in quantum computing. Thank you very much for attention and talk to you soon.